So if you didn't like my lecture from yesterday, I hope this is going to be fine because today I will completely change topic. Nitin will actually explain how the two come together, but you can basically forget everything I said yesterday, except for maybe the last formula, the one about quadratic Carey structures. You just have to remember the shape of that formula because it will pop up again today. So today the topic is the topological recursion a la Énard and Donaldson. So this is the original formulation of TR. So we now go back in time, and topological recursion in this form was discovered in 2007, so more or less 20 years ago, when Énard and Donaldson were trying to understand and basically solve the loop equations in matrix models. And one of their insight was that the formalism that they discovered in the context of matrix models can actually be formalized without any underlying matrix model. And they basically asked the mathematical community, is this interesting in any way? So what I will do today is actually explain to you what this formalism is and give you a couple of examples that are relevant in enumerative geometry, okay? And one thing that I should say is that yesterday I tried to be as general as possible. That is not a big issue with Airy structures. Today, instead, I will focus on what will be essentially equivalent to the quadratic Airy case. So today I will be less general. Everything that I say here can be generalized, but I will not go through this pain on the board today, okay? So let me actually start with the main object of TR, which is the spectral curve. So a spectral curve is just a quadruple that will be like four elements like this, sigma, x, and two objects that I will call omega 01 and omega 02. So what are these objects? The sigma is a Riemann surface. The sigma is a Riemann surface that might be non-compact and non-connected, if you want. So it is possibly non-compact nor connected Riemann surface. X is going to be a meromorphic function. So let me say X, maybe I'll write it as a holomorphic function from sigma to P1. Same as a meromorphic function. Sigma. Omega 01 is going to be a meromorphic one form. So this is a meromorphic one form on sigma. And often we will actually write it as a meromorphic function times dx. So often we'll write omega 01 as something like a meromorphic function y times dx. Okay, so these are the first three data, and the last data is this omega 02, which is it's a very special object. So omega 02 is something known as is a fundamental bidifferential. On sigma, so this is a very special object in the theory of Riemann surfaces that maybe not so many people are familiar with. So what this means is that omega 02 is bidifferential. So it's a differential on, so it's if you want, it's a meromorphic section of sigma squared of the canonical squared, the bidifferential. That it's symmetric with poles only along the diagonal. sorry, with double poles. With double poles along the diagonal. And by residue 1. So if you prefer like some sheaf notation, so what this means is that this is a section of sigma squared, and here you have the canonical box squared, and you have only a double pole along the diagonal. It's symmetric. It's an object like this, and having by residue 1, what it means is that if you take any local coordinate and you express this in local coordinates, you will find something like this: dz1 over dz1 dz2 over z1 minus z2 squared plus something holomorphic. And having by residue 1, it means that the coefficient of this expression is equal to 1. Okay. Is there any question about omega 02? It's a very strange object. Yeah. Yes, I will soon give some constraints. Yeah. So I will. This is my definition of spectral curve. Soon I will define something called an admissible spectral curve, and these are the kind of objects that I would consider.
So the comma that you have in the notation of the better is like a tensor product? No, when you will go one line down, then you do.
This one?
Z1.
Yeah, sorry. This is Z1, comma Z2. So it's a section of sigma squared of the canonical box squared. So you should think of it as if you freeze Z2 is a differential in Z1, if you freeze Z1 is a differential in Z2. Okay. Good. So maybe let me give you one class of nice examples. So if you take sigma that it's compact and connected, say of genus G0. Then whenever you have two meromorph, and let's say that omega 01 is given by an expression like this, what you deduce is that there's a polynomial that in two variables that relates these two meromorphic functions x and y. So in this specific case of compact connected Riemann surfaces, you can think of this theory as being just a theory of plane curves. Okay, and what I want to stress about this example is that for such compact connected Riemann surfaces, these omega 02, like the theory of this fundamental bidifferentials, it's very nice and classic. So one can say that if in this case sigma comes with a Torelli marking, meaning a basis of A and B cycles, a symplectic basis of A and B cycles, then a nice fact is that there exists a unique omega 02, so a unique bidifferential satisfying these properties here, that it's normalized along the A cycles. So there's a unique omega 02 such that if you take the integral of this object along the A cycles with respect to, let's say, the first variable. Oh, sorry. Yeah, let's say with respect to the second variable. So the result here is equal to 0. I will give you an example in a second. Okay. So as Valentin was saying, so usually in TR, there are some conditions that you have to impose here. So let me talk about these conditions here. And first, let me recall some things that we kind of saw in both Drew's and Valentin's courses. So but I just want to set up the notation. So now let's take P that it's a point on sigma. And what I can do, I can always pick local coordinates. So pick local coordinates around, or let's say centered at P. Such that the map X looks like zeta goes to zeta to the R. Okay, so you can always do that. This is called the normal form at P, and this this integer R here. So this is called a ramification index at P, ramification order at P. And recall that we say that P is a ramification point if this R is greater or equal to 2. Okay. So this we saw several times in the previous lectures. And what I want to consider today, so this is the simplification that I was talking about at the beginning of the lecture, that it's related to the fact that we are only considering essentially quadratic area deals in this setting, is that for today, all ramification points are simple. Meaning that R is equal to 2 for all ramification points. Okay. And in this case of simple ramification points, there's well, this is true in general, but there's something nice that you can define locally around each ramification point. So if, say, if P is a simple ramification point, meaning that X is locally zeta maps to zeta squared, then you can locally define around P an involution. So you can define sigma that it's going to be an involution on the Riemann surface locally around P, which is just the involution that maps the local coordinate zeta to minus zeta. Okay. So this sigma P is it's going to be an involution that it's only locally defined around P. This is going to be important for me. So the picture that you should have in mind is basically the following. So imagine sigma is something like this. Here you have X. This is your ramification point P. And then sigma is essentially going to be the map that is exchanging the two sheets. So sigma is exactly this map here, and it's only defined locally around P. Okay. Do you have any question about this setup? It doesn't matter. It doesn't matter. In this for this part here, it doesn't matter. The nice thing about having a compact Riemann surface is that this omega 02 object is maybe less strange. As soon as you fix a Torelli marking, is uniquely given. Okay. You have a canonical choice. Okay, so today I'm going to restrict to functions this first data here on the spectral curve X that only has simple ramification points. But this is not enough to have a well-defined theory. I will also have to suppose something about omega 02. So what I'm about to say is some other set of conditions on omega 02. And these conditions are only going to be relevant. They're only going to be local conditions around a simple ramification point. So again, around P simple ramification point. What we can consider is the following expression. Take omega 01 of Z minus omega 01 of sigma P of Z. So this is maybe a weird thing to consider, but you will see very soon that we will we will consider these kind of expressions several times. So take this expression here. This is only locally defined around P because this involution is locally defined around P. But what we can do is pick this local coordinate and expand. And because I'm taking this, this difference here, when you take the expansion, you will only end up with only even powers, so in the local coordinate. So this Lorentz series will look like this. Will be a sum over k greater or equal than a certain value kp. And here you'll have some constant that depend on e and k. They don't really matter, but the expression will be something like this. Okay. So here I'm just taking the Laurent expansion around P in the local coordinate zeta. And because I'm taking this specific combination, I only have positive powers. And here I'm setting up everything so that the coefficient here, so this Cp Kp is different from 0. Okay. And this is the only thing that matters. So what matters here is this Kp, which is just the order of vanishing of this combination at P. So yeah, maybe let me move there. So in that situation, we say the following. So definition. So we will say that a spectral curve S with only simple ramification points is admissible. If for every P that it's a ramification point, I will use this notation RIM for the set of ramification points. So this is called admissible if for every ramification point, this integer k p is less or equal to 1. Okay, and this is just like because of the way I set up the notation. So this is equivalent to say that the order of vanishing at P of this expression omega 0, 1 minus essentially the pullback of omega 0, 1, this is less or equal to 2. Okay. This 2 is coming from the fact that here I double the index, okay, but nothing crazy. So essentially what I want is that omega 0, 1 has some either zeros or poles, but the zeros are not too high in the order. And I will actually want to say something more, so I will have a classification of this type of ramification points. So I will say that if Kp is equal to 1, then P is of airy type. So this is the same as saying that this specific expression has a 0 of order 2 at P. If Kp is equal to 0, then I will say that P is of Bessel type. So this condition is the same as saying that this expression is regular at P and non-vanishing. And if instead Kp is less or equal than -1, then I will say that P is irrelevant. Okay. So this is not too important, but somehow the most important condition is that I don't want this expression to have zeros that are of order too high. Okay, so let me give you some more concrete examples now of admissible spectral curves. So the first example is the one that everyone loves, which is called the airy curve. So as a plane curve, this is the one given by a half y squared minus x equal to 0. And this is also, well, among other things, is the reason why this curve is called the Airy curve, because this is just the semi-classical limit of the Airy differential equation, okay? So you can convince yourself that a plane curve given by this has a compactification, which is given by P1. So the underlying curve is P1. And the two functions x and y can be rationally parameterized in this way. X is 1 over z squared, and y is equal to z. Okay. And well, P1 is compact, and there's actually no Torelli marking to pick. So what this fact here is saying is that there exists a unique omega 02 on P1, and this is exactly given by well, the expression that you can suspect. So this is on P1 is just dz1 dz2 divided by z1 minus z2 squared. And here, of course, that is the global coordinate on P1 minus infinity. Okay, that's it. So this is the Airy curve, and you can check that, well, from this expression, you can see that there are only two ramification points. So one is z equal to 0, and the other is z equal to infinity, right? And from this expression here, so I just erased this, but you remember that omega 01 is defined as y dx. So in this case, this is z squared dz. Okay. And you can see that omega 01, well, you have to, so maybe I should say here the local involution is actually global, is z goes to minus z. And if you look at this, you can realize that this is a ramification point of Airy type, while this ramification point here is actually irrelevant. Okay. So omega 01 is always defined as y dx. So I can either give you omega 01 or I can give you a function y, and then omega 01 is defined in this way. Okay, so this is the Airy curve. This local behavior is called of Airy type because it's related to this model here. Okay, and you can guess now what the second example is going to be. This is going to be the Bessel curve. And this is given by the following equation. So x y squared minus a half equal to 0. And again, the name Bessel comes from the fact that this is the semi-classical limit of a Bessel differential equation. And again, here you have that sigma is just a P1. And you can rationally parameterize this in a similar way. X is a half z squared, but now y is equal to 1 over z. Okay. So now if you do the computation, you can see that omega 01 in this case is just dz. And omega 02, it's again the same one. And you can see that once again, you have two ramification points, one at z equal to 0 and one at z equal to infinity. And this is of Bessel type. Because omega 01 is regular and non-vanishing at 0, but infinity is instead an irrelevant ramification point. Okay. At this stage, it's not clear why I'm calling this irrelevant. You will see in a second why this is irrelevant. Okay. Good. I want to give you two more examples. So one is a non-compact, well, two are non-compact. One is called the Mirzakhani curve. And this is the one given by well, sigma equal to the complex plane, and x is equal to z squared over 2 once again, but y is something more complicated, is the sine function, sine of 2 pi z over 2 pi. And you can see that I excluded here infinity because it's an essential singularity for y, so it's bad. So this is non-compact, but it basically, like, if you join infinity, it basically behaves like a P1. So in this case, it's very natural to consider omega 02 as the one from P1. So okay. And you can check that here the only ramification point is 0, and it's of airy type. And let me give you 2 more examples. So one is called the Lambert curve. Here, sigma is c minus the negative real axis. And x is equal to z minus log of z, while y is equal to just z. And omega 02 is, again, the usual one. And here you can check that the ramification point is at z equal to 1, I believe. I think so. And it's of airy type once again. Okay. And one last example, it's the Weierstrass curve. So this is a compact example where sigma is a torus, c over z plus tau z. And well, I can actually represent this in this way: y squared equal to 4x cubed minus g2 of tau x minus g3. No, sorry. Yeah, right. Okay. And here, if you want to parameterize x and y, in this case, you can use the Weierstrass P function and its derivative. And this is a compact case, and because I presented sigma in this way, it comes with a canonical A and B cycles. So thanks to the fact that I stated before, you should have a unique omega 02 in this case, and it's given by the following formula. So omega 02 in this case, it's once again the Weierstrass P function. So it's Weierstrass P at Z1 minus Z2. And you have to remove from it the following part. It's pi over the imaginary part of tau. And this is another fun example. It's a derivative in z, sorry. Okay, so before giving you the definition of topological recursion, I actually want to talk about this omega 02. Because you see, in all these examples, in some way, you know, x and y, the role of x and y, it's kind of transparent. They're, at least in the compact case, they are essentially the variables of a polynomial defining your curve. But what about omega 02? It seems like a very strange object with this strange conditions on this double pole along the diagonal and so on. So what I'm about to say is something kind of classical from the theory of Riemann surfaces, but maybe not so well known. So I'll spend some time explaining this. So what I want to explain to the now it's what is the role of this omega 0, 2. And you will see that omega 0, 2 is a very magic object. So well, let me start with a definition. So let's say given omega 0, 2, that satisfies the property before, and let's also fix S, which is a finite set of points on sigma. It will soon be the set of ramification points, but what I'm about to say holds in general for any set of points. So if I fix S like this, and let's say I fix alpha, which is a meromorphic one form on sigma, I'm going to define an operator that I will call B hat relative to this set of points S. And this is going to be an operator that takes as input a meromorphic one form, and it spits out another meromorphic one form. So what I'm going to tell you is what it's the meromorphic one form associated with alpha. And this is by definition the sum over all points P in S. And I have to take the residue at Z equal to P of the integral from P to Z of omega 0, 2. I will fill the first slot with Z prime here, and I integrate the second slot. I multiply by alpha, and I take the residue, okay? So this is the definition. Yeah. S is finite, yeah. Yeah. So before telling you something more about this B hat, let's stare at this and see if it makes sense. So omega 0, 2 is a bidifferential. So what I'm doing here, I'm taking a bidifferential, I'm integrating it in the second variable. So the result here in parentheses is going to be a differential in Z prime and a function in Z because I just integrated it. So this is a function in Z. I multiplied by alpha, which is a one form. So this whole thing, it's going to be a differential in Z prime and a differential in Z. I'm taking the residue in Z. So the result of this is a differential in Z prime. Okay. So this B hat takes a meromorphic one form and it spits out a meromorphic one form. Cool. So this is the definition. So what can we say about this operator? Oh, by the way, here I'm calling it B because it stands for Bergman. So many people often call omega 0, 2 the Bergman kernel. Apparently, this has nothing to do with Bergman, but people call it Bergman anyway. So I'll call B this operator B for Bergman. Okay, so what I want to discuss is a couple of magical properties of B hat. And so these are three properties that I want to discuss. So the first one is that alpha and B hat S of alpha, they have the same principal part at each point P in S. Okay, so principal part here is a fancy word for the polar part. So if you expand in Laurent series around P, the principal part is everything that it's polar. Okay, I will actually not prove this, but if you want, you can try to do this exercise. It's not that difficult. One way of doing this exercise is just expanding everything in local coordinates. And here, the most important part is that omega 0, 2 has this nice properties that around each point in local coordinates, it behaves like dz1, dz2 divided by z1 minus z2 squared. Okay, so you can use that and just show in coordinates that these two meromorphic forms have the same principal part at every point P in this set S. Okay. Oh, that's true. Thank you, thank you. So here I will only assume that this is a meromorphic one form, that it's residue free. At every point. This was not in Vincent's lectures. I can blame Vincent. Okay, thank you. Cool. So the second property is the fact that B is actually a projector. So if you take B hat and you compose it with itself, then the result is B hat again. So this is the same as saying that B is a projector. And I will just give a quick proof of this because it's very easy. So from point 1, you can see that alpha and B hat of alpha, they have the same principal part. So if I take the difference, so this is holomorphic at P for every P in S. So now if I apply B hat again, you'll see that I have B hat of alpha minus B squared, essentially. But here I just applied B hat to something holomorphic at P, and you can see from the definition that if alpha is holomorphic at P, then this residue just vanishes, okay? So the result here is 0. So you get this statement here. Okay. And the third property that I want to discuss is, for me, the most magical property, which is, I like to call it local to global. And this is the fact that even if alpha is not a globally defined meromorphic one form, but you can see that in the definition of B hat, I don't really care about alpha everywhere on sigma. I only care about the behavior of alpha around the ramification, around these points P. So I can actually take alpha to be just a germ of a meromorphic function. So even if alpha is the germ of a meromorphic function, of a meromorphic form, then B hat of alpha is actually globally defined. So this is an amazing property because this B hat operator, it's an operator that allows you to take just something that it's only locally defined around each P, and with this operator B hat, you just globalize it. It's an amazing thing, in my opinion. And well, maybe let me say one more thing. So if sigma is a compact Riemann surface, this operator B hat is actually something that it's sort of classical in the theory of Mittag-Leffler residues and so on. So maybe let me say like this. So if sigma is compact with a Torelli marking, one can actually give a characterization of B hat of alpha. So then B hat of alpha is the unique one form with the same principal part as alpha at P in S, and normalized along the A cycles. meaning that in this specific case, if you take the following integral of b hat of alpha, then this is 0. Okay. Cool. Do you have any question about this b hat operator and its properties? It's very mysterious in some sense, but it's one of the key properties of topological recursion. Oh, maybe before going on, let me maybe say something about this. So this projection property, well, the fact that B is a projection operator is going to be very relevant, and I will say that alpha satisfies the projection property if alpha is equal to its projection. So if alpha satisfies this equation. Another way of saying this is that alpha lies in the image of b hat. Okay. Whenever this happens, I will say that alpha satisfies the projection. This property here. Well, it comes from the properties of omega 02, which is characterized as a bidifferential with a double pole along the diagonal and by residue 1. It comes from this. So, yeah, I don't know. Maybe, yeah. I don't know how to characterize it in a different. Maybe one thing that I should say is that in this compact case, there's actually something even more beautiful that you can say. So on this space of germs of meromorphic functions, of meromorphic forms that have 0 residue, you can actually define a symplectic pairing. And this symplectic pairing has a very natural Lagrangian subspace, which is the space of holomorphic forms. And what this b hat here is doing is just giving you an opposite polarization. And the fact that this opposite polarization is also Lagrangian is a consequence of Riemann bilinear relations. Okay, I'll not show this because it's not so relevant, but this is to say that this b hat has a lot of properties in common with very cool things about the theory of Riemann surfaces in the case when sigma is compact. But in this setup, I actually don't need compactness. These properties here will be enough for me. Okay. Good. And so just to show you how you can use this b hat, I will state one definition and one lemma. So as we said here in property 3, b hat is extremely nice because it allows you to globalize some only locally defined one forms. And this is exactly what we're going to do. So if you fix a point P on sigma, I will, and let's say zeta is a local coordinate centered at P. I'm going to define for every k integer the following differential. So define psi p comma k to be the differential that you obtain by globalizing something just local, which is the following. So here I'm taking b hat just with respect to the set that contains only p. And here I'm going to globalize the differential d zeta over zeta to the k plus 1. Okay. This is the definition of a differential that it's uniquely specified by our choice of omega 02, this integer k, and the point P. And essentially, by definition, so this is a differential that locally around, so locally at P, it behaves like d zeta over zeta to the k plus 1 plus something holomorphic. And this holomorphic part is determined by whatever I choose for b hat, for omega 0, 2. And one reason for caring about this is the following interesting lemma. So whenever I fix a meromorphic one form alpha, I can actually express b hat of that one form in a basis given by these differentials here. So I fix S a finite set as before, and what one can show is that this is equal to the sum over P in S and the sum over a natural number of some coefficients that I can denote like alpha P comma K times psi P comma K at Z. And the important point is that there are only finitely many non-zero coefficients. Okay. So at the moment, this might be a bit obscure, but you can see how powerful this is. So I'm taking meromorphic one form. It can be whatever. But as soon as I take its projection, I can express it as a finite linear combination of some very natural one forms that are these CP comma K. And if you want another way of saying this is that whenever I have a one form that satisfies the projection property, I have a natural basis where I can expand this given by this one forms. Okay, it's a nice way of taking something that it's a one form, so it's very hard to control. But now I'm just saying that you can control it with finitely many non-zero coefficients. It's a very nice thing. Okay. Do you have any question about this? Yeah, exactly. Yeah, exactly. So if there are no more questions, I can finally define topological recursion. All this setup was to now define topological recursion and have some, and immediately see some nice properties that it satisfies. Okay. So let's now fix an admissible spectral curve. So this is the data of sigma, x, omega 0, 1, and omega 0, 2 with only simple ramification points. And admissible. So what topological recursion is providing to you, it's a collection of multi-differentials that are recursively defined from this data, and the recursion is going to be a recursion on 2G minus 2 plus n. So we're now going to define a system of multi-differentials for G greater or equal to 0 and greater or equal to 1 with 2G minus 2 plus n, and it's strictly positive. And these are going to be defined recursively as follows. So omega gn of z1 to zn is defined as the sum over p that runs over the ramification points. And then I take the residue for z at p of a certain expression that I will define in a second called the recursion kernel. It depends on z1 and z. And I multiply that with an expression that that should be familiar from yesterday, so a specific combination of these guys. So the first one is omega g minus 1 n plus 1 at z, sigma p of z, and then z2 up to zn. And then I have a sum over the splittings of the genus, so g1 plus g2 equal to g, and I1, disjoint union I2 equal to the set from 2 to n. And then I have the quadratic term, omega g1, 1 plus I1, evaluated at z, and then the variables associated to the first splitting of the markings. And omega g2, 1 plus I2, and then I have sigma p of z and zi2. Okay. So I will comment on this in a second, but I still have to tell you what this guy here is. So k p of z1, z2. This is by definition half the integral from p to z of omega 0, 2 in the variable z1 and then the one that I integrate. And here I divide by omega 0, 1 of z minus omega 0, 1 of sigma p of z. Okay. Thank you very much. Yes. And here I have no 0, 1s. Okay. So what I mean by this is that in this sum, I allow some of these omega gns to be of type 0, 2, but I don't allow them to be of type 0, 1. And because I exclude 0, 1, this is actually a recursion. So everything that appears on this left-hand side of the equation has 2g minus 2 plus n that it's strictly less than 2g minus 2 plus n. You understood what I mean? Can you repeat, sorry?
Of omega.
Yeah?
It will be size of.
Yeah, thank you. So here I mean size of I1 and size of I2. Thank you. Okay, so before giving you some properties of this, let me pause for a second and think about this equation. So first of all, recall that sigma of p is the local involution around the each simple ramification point. So every time you see sigma p, that is only locally defined around p. So this kp here is actually globally defined in z1. Is that z1? So it's globally defined in z1, but it's only locally defined in z. Sorry, yeah. It's only locally defined in z. And we will see soon that all these omega gns are globally defined. So by recursion, we will see that this the expression here inside this bracket is globally defined in z2 up to zn, but it's only locally defined in z. This is fine because at the end of the day, we are going to take a residue. So having it locally defined around the ramification points it's all we need to take a residue. Okay. So this is the first observation. The second observation is that, so what is this expression? So this expression is actually one form in Z1 and minus one form in Z, okay? So if you want, this is a section of the canonical in Z1 and the anti-canonical in Z, while the expression here in the bracket as a function of Z is actually a quadratic differential because Z appears in these two slots. So it's a one form in Z times a one form in Z again. So this is a quadratic differential. And so as the whole thing inside the residue, it's going to be minus one differential times a quadratic differential. So it's actually a differential, and then it makes sense to take the residue, okay? I think this is all I wanted to say. Do you have any question about this formula? Yeah. thank you. This is what I wanted to say. Yeah, thank you. So indeed, if you remember yesterday, I had actually 3 terms, and here I only have 2. So the only difference is that yesterday I was taking only stable terms in this sum, while here I allow 0, 2, but 0, 2 is unstable. So this is the main difference. But the equation from yesterday had 1 more term, and this term is actually hidden in this. So one way of rewriting this equation is by actually excluding both 0, 1 and 0, 2. So if I restrict to all stable terms here, this term here will now be equal to the term we had the other day, but I cannot just get rid of it. I have to add it back. So I can restrict to only stable terms here, but then I will have to add something that looks like this. Have a sum from 2 to n. So because if you think about when can you get 0, 2 is exactly when one of these 2 sets has a single element and the associated genus is equal to 0. So this M runs over all possible ways of selecting one element from here. And what I will get is something that looks like this. So it's omega g n minus 1, z, and then here I have z2, I skip zm, all the way up to zn, times omega 0, 2 of sigma p of z, comma zn, plus the one that you obtain by inverting the role of z and sigma p of z. Okay. So if instead of including 0, 2 here, you exclude it, but you add this back, you get exactly the formula, the shape of the formula that you saw yesterday with 3 terms. Okay, thank you. Do you have any other good question? Yes, I will comment on this in a second. Yeah, thank you. So let me now give you some properties about this. So maybe I'll keep this property here. So the theorem, I will say that there's a theorem which is due to Einar and Dorantin in their first original paper. And it's a bunch of properties satisfied by this omega GNs. So maybe the first property is that actually we can restrict the sum to only non-irrelevant ramification points. Remember that irrelevant ramification points are ramification points for which this expression here has poles that are very big. And you can kind of see why this is true, because if this thing has poles that are too big, there's no chance of getting a residue, okay? So in this sum, instead of summing over all possible ramification points, I can just sum over the ones of Airy type and Bessel type, okay? So everything that it's irrelevant will just contribute 0 to that residue. Okay, and let me call maybe rem plus the set of non-irrelevant ramification points. Cool. So this this is just a silly remark. The main theorem is actually the following property. So the main point is that omega gn, this is an n differential, meaning it's a differential on in each one of the n variables, that it's symmetric. It has poles only at the non-irrelevant ramification points of order less or equal than 6g minus 4 plus 2n. Okay. And what is magic about this statement is that the omega GNs are actually symmetric. So as you can see from the definition, and this was the same observation in the context of area structures, we have a recursive formula that is highly non-symmetric in all the variables. Z1 is playing a special role, but nonetheless, the final result is symmetric. And to prove that this is symmetric, like you can do it by hand. It's extremely painful, so please don't do it. But symmetry here, for the symmetry here is really important that we have an admissible curve. So if this expression here, omega 01 minus omega 01 of sigma p has zeros that are too high, you will not get symmetric objects. So this admissibility condition was important not for having this formula here, but to get something that is symmetric in the end. Okay. Okay. And the third property I want to say is that this omega GNs they have a vanishing residue. At the these ramification points. And the fourth property is that they satisfy the projection formula. Sorry, they satisfy the projection property with respect to the set of non-irrelevant ramification points. Okay, so this is to answer your question why this B hat is relevant. And maybe let me just quickly comment on this last property here. And if you remember the definition of B hat, this is essentially immediate. So property 4 is just a consequence of the fact that by definition, these omega GNs are defined as B hat at the ramification points of what? Of whatever it's in the denominator of the kernel. So omega 01 of Z minus omega 01 of sigma P of Z times this big parenthesis here. Okay. As a function of Z1, actually. So Z2 up to Zn act as spectator variables in this case. So is this clear? So if you put together the form of the kernel here with the definition that I gave before of this B hat, you immediately get this formula. So by definition, omega Gn satisfies the projection property because, right, it's not immediate, but sorry. But one can show that it satisfies the projection property using this formula here. Okay. Sorry, I thought it was immediate. It's not immediate, but you can prove that it satisfies the projection.
Apply again. You just apply the projection.
Oh, true. Yeah. Thank you. Yeah. This is blackboard radiation again. Yeah. Okay. Do you have any question about this? So at this point, everything seems a bit mysterious, but maybe let me first give you a glimpse into the connection with area ideals, and then I will just give you some examples. So this projection property is extremely nice because of the lemma that I erased. So an immediate corollary from this is that we can actually write down these omega GNs in a nice basis and at the end of the day, we only have to care about finitely many non-zero coefficients. So remember that whenever you have something that satisfies the projection property, you can write them in this basis of differentials that I called psi p, comma k. So what we have is that these omega GNs they can be written as a sum over, well, I can do this for every single variable because they're symmetric. So I can write them as a sum over P1 over up to Pn that are non-irrelevant ramification points. And then I have K1, Kn that are greater or equal to 0. And here I will have some coefficients that I will call f, g, let's say A1 up to An. And here I will just denote Ai to be the pair Pi comma Ki. Okay. And so I have this times the basis of differentials that I defined before. So this psi Ai in the variable Zi. And what is nice about this formula is that here you have only finitely many non-zero coefficients. So as before, the sum over the Ki's is it truncates. Okay. And maybe let me tell you what's the spoiler for Nitin's lecture. So this FG A1 up to An will be coefficients of a partition function of an area DO, of actually a quadratic area DO. And so you can see, for example, that in this case, the index set that I used yesterday is just the set of ramification points, positive ramification points times the integers. Because all of these guys are exactly indexed by this. Okay, so this is what essentially Nitin will show you in his first lecture. Do you have any question? Okay, so I have 15 minutes, right? Okay, so in this last 15 minutes, I want to say two things. So first of all, I want to show you how this crazy formula has actually a very nice graphical interpretation. We basically saw this already the other day, but let's repeat this because I think it's good to demystify this formula. So let's try to compute together omega 1, 2. Okay. So omega 1, 2, what I have to do is, from the formula that I just erased, what I have to do is essentially write down all possible ways of taking out a pair of pens from something of genus 1 with two, let's say, boundary components, so that whatever it's left, it's not a disk. Okay. So let's try to do this together. So let's first start from something of genus 1 with two boundary components, let's say labeled by Z1 and Z2. And let's try to write down all possible pairs of pens decompositions that bound at least Z1. So one way of doing this is as follows. So here the rules is that I have to put Z1 on the first boundary component, and whenever I take a pair of pens out, I have to label the two remaining one with Z and sigma P of Z. And so what can I add here that it's not a disk to get a surface like that? Well, I can add another pair of pens like this. And here I will label this as Z2. Or I can add a torus with one boundary component and cylinder. It would be Z2, Z1, Z, and sigma P of Z. But this combination here is not symmetric, so I can also do the opposite. Here I have Z2, And here I have Z and sigma P of Z. Okay. So this is the picture that you associate to something of genus 1 with 2 mark points. And once you write this down, you can now replace every single element in this formula with whatever the picture is telling you to do. So here, this guy, it's always going to be replaced by the sum over P, the set of ramification points, residue at Z equal to P of the kernel with variables Z1 and Z. And here instead, for example, this will just be omega 0,3 at Z, sigma P of Z, Z2. This term here is just omega 1,1 of Z. This one is omega 0,2 of sigma P of Z and Z2. And you can imagine here I have instead omega 0,2 of Z, Z2. And lastly, this is omega 1,1 of sigma P of Z. Okay. So don't be scared about the formula, it's just about Pence decomposition. And plus this substitution rule. Okay. Now, this is all nice, but again, a nice theory, it's useless unless it has nice applications. So let me conclude with some applications. And by the way, if you want to play around with this definition and some examples of spectral curves, if you go to my website, there's a link to my GitHub. You can download a Mathematica file for computing omega GNs, and you can play around with that if you want. Okay, so let me conclude with some examples. So these examples are exactly the ones that I told you about at the beginning. So let's start with the one we all love, which is the Airy curve. So from the Airy curve, I can now compute all these omega GNs. And I will just give you some examples so that you can, if you want to do an exercise, maybe you can try to compute for the Airy curve omega 0,3 and omega 1,1. And I also give you what the answer should be. So this should be minus dz1, dz2, dz3 divided by z1 squared, z2 squared, z3 squared. And omega 1,1 should be minus dz over 8z to the 4. Okay. You can try by yourself. It's a bunch of residues. It's nothing too crazy. But what is amazing about this is the following theorem that has been proved 1,000 times. And the theorem says that if you take the Airy curve and you compute these omega GNs, these are actually generating functions for psi class intersection numbers. So you get something like this, sum over K1 up to Kn that are positive, and then here you have integral over M, G, and bar of psi class intersections with some double factorials. And you keep track of them with Zi to the power 2Ki plus 2. Oh, sorry, and there's a minus 1 to the n. I checked this morning. I'm like everything that I'm saying here is probably wrong because of some powers of -1 and powers of 2. So you should try and double check. But I think if you take this formula, you can deduce from this that, for example, here, the integral over M0, 3 of nothing is 1. And from this, that the integral over M11 of psi 1 is equal to 1 over 24. And what is nice about this is that, well, this theorem together with the definition of these omega GNs gives you a way of computing recursively these psi-class intersection numbers. And this recursion is equivalent to the one that I showed you yesterday. Maybe one nice thing that I should say is that if you remember the recursive formula that I showed you yesterday is very like messy. While here, I only have to tell you this general formula for the omega GNs, and I have to tell you the data of the area curve, which was something very easy. This data of a half y squared minus x equal to 0. So one can say that all psi-class intersection numbers are just contained in this simple equation. I will maybe skip example 2, which you can imagine very well. So if let me just say it in words. If I take here the Bessel curve, we'll have some different examples here, but the theorem will be that the omega GNs computed from the Bessel curve give you intersection numbers of psi classes with the theta class that I mentioned yesterday. So maybe let me do another example, which is the Mirtahani. So remember, the Mirtahani curve is the one where x is z squared over 2 and y is equal to the sine function. And you can compute omega 0,3 and omega 1,1 in this case as well if you want as an exercise. So this is equal to the area one. Is minus dz1, dz2, dz3 over z1 squared, z2 squared, z3 squared. But the first interesting example is the 1,1 case. So this is going to be equal to minus 1 over 8z to the 4. And here, I remember, like pi squared and something. Plus pi squared over 12 z squared, easy. And you can go on. You can write down a program to compute these omega GNs and compute as many as you want. But the main theorem in this case is that these omega GNs are instead generating functions of Weil-Peterson volumes. So the statement here is that these guys are equal to a sum over, again, k1, kn, greater or equal to 0. And here you have an integral over mg n bar of exponential of 2 pi squared kappa 1. So this is the kappa class that you saw in Drew's talk, times the same expression with the psi classes. And I will conclude with one last example, which is the Lambert curve. Remember, this is when x is equal to z minus log of z, and y is equal to z. So here, sorry, I also have a minus 1 to the n. So in this case, I will not give you examples of the omega GNs. You can try to compute them by yourself. But what I want to tell you is what is the enumerative geometric meaning of the associated differentials. So the theorem here is that these omega GNs are generating function for simple Hurwitz numbers. So this is a sum over partitions of n. And here you take the connected Hurwitz number. I will say exactly what this is in a second. And here you have a product from 1 to n, mu I exponential of mu I times x of zi dx of zi. So here, maybe let me say
mu it's a sorry, mu is a partition of length. Mu is a partition of length n, sorry. And what these numbers are, these are simple Hurwitz numbers. So these are the number of covers of P1, where you have a ramification points whose ramification profile is given by the partition mu over, let's say, 0. And every other ramification point is just simple. Okay. And the last remark that I want to say is that all these theorems, they connect essentially this topological recursion with some intersection theory on the moduli space of curves. This is not quite intersection theory, but if you use the ELSB formula, you can also write this omega GMs as some intersection numbers with the Hodge class. And Nitin in his last lecture will actually show you how you can basically prove this theorem, these theorems using this formalism. Okay, I think I'll stop here. Thank you.
In those cases also, like, can we have similar interpretation in terms of Hurwitz numbers?
No. Well, yeah, so all of this have also some different interpretations, but I mean, it's not really. So this case here, when you take the Laplace transform, you can get exactly the Weil-Peterson volumes. So if you take Laplace transform, you can get rid of this double factorials, and you get exactly Weil-Peterson volumes. If you do it here, you get the Kontsevich volumes of the moduli space of Strabel differentials. But in none of this, you actually have an interpretation as Hurwitz numbers. But this case has an interpretation as Hurwitz numbers. What I might say is that basically all Hurwitz problems where you have one partition that it's free and the rest has like a fixed behavior, they can be computed by topological recursion with a formula like this. So for example, if you take, let's say, this curve here, it's the same, but here you put z to the r, then you will get Hurwitz numbers that are called R spin, or let's say R+1 completed cycle Hurwitz numbers, where you have this generic behavior over, let's say, 0, and everything else is a completed cycle that it's an R+1 cycle with some completion. It's the type of cycles that Dhruv mentioned at some point. But it's not true that every spectral curve has an interpretation of Hurwitz numbers, but every Hurwitz number with this specific type can be computed by topological recursion.
They also have like some sort of interpretation of some spectral.
Yeah, so
this is just special.
Yeah, so every Hurwitz number where you have one partition that is special and everything else as a fixed behavior can be always computed in this way. If you start allowing like more, like, I don't know, like double Hurwitz numbers, it's much more subtle. Yeah. I don't know on the nose, but probably yes. If I have to guess, I would say yes. I never saw it this way. Yeah, indeed. Like, is this true? If the exponential appearing here, it's related to the fact that for simple Hurwitz numbers, the weight is essentially the exponential. Yeah, yeah. I don't know, but probably yes. That's maybe what I can say. Thank you.